Hello everyone, myself Subham Sharma. I am third year and undergraduate at IIT Roorkee, and today I am going to talk about on a topic which is named image and pattern recognition with Fourier transform. Now today we will be exploring the significance of Fourier transform in modern technology. So first, we are going to understand what is Fourier transform and the other aspect of these, like what is the mathematical foundation of this, and what are the different types of Fourier transform, and how noise reduction is uh, used, and image comparison. Some key concept in image processing are the frequency domain analysis, which consists of analyzing images based on their frequency component reveals critical features. The other is the phase information. Fourier phases are essential in capturing characteristics of physical domain fluctuations. And the third is the pattern recognition. Fourier transforms significantly aids in the identifying and recognizing pattern within images. So next is, so here, as you can see, this is a square function, which has a time period of 2 pi. So, according to Fourier, this square function can be obtained from summation of many infinite sinusoidal waves, like this is shown. Like here, if we add these two sinusoidal waves, we will get this. If we add these three sinusoidal waves functions, and we will get this. Likewise, if we add all these, we will get this, and adding infinite amount of infinite sinusoidal functions, we can get exactly the this square wave. Now we will talk about Fourier transform. Uh, the this square wave, how can we show this in the form of amplitude and phase form? These amplitudes show the amplitude of those sinusoidal waves from which it is made, and these are the phases. These are the phases. These phases deflect from each other due to the difference in the phases of the uh, parent waves, sinusoidal waves. So this is for a Fourier transform, and this is for inverse Fourier transform, in which if we have the amplitude and the phase of the uh, infinite sinusoidal waves, we can get, after adding these, we can get the original square wave. So in this slide, I'm going to tell that how Fourier transform and infinite Fourier transform can be mathematically represented. So this is a few Fourier transform in frequency domain. So this is the integral of fx from minus infinity to infinity of fx e power minus I to pi mu x dx. So here mu is frequency, and minus infinity to infinity consists of infinite number of sinusoidal waves. Like in the same manner in inverse Fourier transformation, this both look same, but the difference comes, we swap these two. Okay, other things are the same. Like here are some examples of Fourier transform. Here we have a D, uh, DC, DC signal, which is constant from minus infinity to infinity distance. After taking the Fourier transform, we will get a delta function at mu is equal to 0 with a in particular magnitude, not defined here. In the second example, we have a delta function with not a defined magnitude. If we took the Fourier transform of it, then it will show a constant wave from minus infinity to infinity frequency. Like in the third example, if we take a square wave, this is the result we will get after taking the Fourier transform of this. This is a sine C wave. Now, so now we will talk about convolution. This is very important in recognition, and it has a very strong relation with Fourier transform. So what is convolution? Convolution refer to both the result function and to the process of computing it. Like this. It is defined as the integral of the product of two functions. Here, fx and hx are two spatial functions in spatial domain, and their convolution gives us gx. So we have uh, represented these convolution in the form of integration minus to infinity d tau. So, what does this integration represent? So we have represented the f function in the form of tau and its function the tau. After doing time shifting and time scaling, the h tau will flip to this side and it will shift to little this uh, uh, making x minus tau. So what we will do with it? Then taking x tau, we will move this from minus infinity to infinity, and after convoluting it, we will get this green part. So this is the process that the integration was showing. So there is another one example. Here we have take two functions f and x in spatial domain, both having a square wave. After convolving h with f or f with h, doesn't matter. We will get a rectangular wave. It will always be same. So next, so here uh, uh, this is the expression for convolution for getting gx. So now taking a Fourier transform of gx, g of u in the frequency domain, minus infinity gx e power minus I to pi mu x dx. So now putting the value of gx and changing the value of x so that these two integration can be separated out. So as we can see, this expression is like of f of u, Fourier transform in the frequency domain, and after changing x minus tau and replacing it with any constant y, uh, we can see that the h is related with y and there is dx, but dx is from minus infinity to infinity, so it doesn't matter. You will get a transfer function h in the frequency domain. So what does this represent? This means that convolving two spatial function, we can get gx, or we can multiply two Fourier transform function to get a gu. This is shown here, what I told you. Like in spatial domain, if we convert two functions, we will get gx. Uh, Doing the same thing in frequency domain, we can multiply these two Fourier transform function, and we can get the same function gu. You get g in the frequency domain. Or like in the spatial domain, we can multiply these two spatial function to get gx, or to get the same output, we can convolve two Fourier functions to get gu. Like this is represented here. Like gx is equal to we can get gx by convolution of f of h, taking Fourier transform of these two, and take multiplying these Fourier functions, we can gu. And after getting gu, we can take inverse Fourier transform and we get gx. So the point is now is why we are doing this, why we are doing these too many steps, if it is possible straightly. So the thing is, we have more optimized codes to do Fourier transforms. Like if we have large number of kernels, so it becomes complex to convolve many functions. So we first take the Fourier transform of all the function and then multiply it, and the output that we get, we take inverse Fourier function of that. So next, here we have a f function in the spatial domain, and as we can see, it has noise in it, and there is a Gaussian kernel. Uh, so we have to convolve it. So I discussed earlier, taking an easier path. We took Fourier transform of both these functions. So in frequency domain, as we can see now, we have our area of interest oriented at a very small part, and Here we can see v- very two small spikes. These are the noise. So it is compressed now, and taking the Fourier transform of the Gaussian kernel, it doesn't change anything more. So after multiplying these two, we get FUHU. So as we can now see that we don't have any noises in the output. And taking the inverse Fourier transformation of the output, we can see now we have a Gaussian blurred, and this is the graph in black is the output, and the green lines it's showing the original. So this graph is showing the difference, right? How the GX got changed if we did the Fourier transform of the inputs. Next. So here we have 2D Fourier transform. As we know, the images that we see in real life are in 2D. So we have to now understand Fourier transform in 2D. So here is a double integration minus to infinity, x and y, two coordinates, and this is the u and v frequency in x coordinate and y coordinate, and the same expression for the inverse Fourier transformation. And these are some of the examples. So in this example, it is showing a cosine wave. So we can see we get three dots after doing the after taking the Fourier transform of these two. So, why we are taking log here? Because in the Fourier we will get huge intensities. So taking the log we can uh, uh, compress it. And like here, after taking large frequency, we will get as it is 3 points, but the space between them get increases. And after adding all these two images, we get 5 points. Next. The other examples like in this photo, we have a small rectangle. So we are getting these two lines. What is this? What this is representing is we are getting here light with high frequency. This is because of the sharp edges here, and here this frequency we are getting due to this the length of the can be said as chalk. Like here, we have a symmetric object, so it has a symmetric frequency, and outside this, it has a low frequency. Here, we can get the magnitude of the frequency according to its color. In the second example or third example, we have a cube. So here, we have three frequencies. We depicts height, length, and the breadth. This and if we get a complex image, we get this means after doing Fourier transform at on complex images, we don't get as much clear results. Like in this, we get many frequencies because of the horizon, this complex image, and in this image we have only noise, but we are getting some output. This is because due to high frequencies. Now let's talk about filtering. We after applying Fourier transform on this, we get this, and after passing it through a low pass filter, means only letting low frequencies to enter, we get this, and after getting an inverse of this, we get again a picture, but it is not visible here. We will not get a smooth image of that. We would be able to see small boxes, as a picture is a combination of rows and columns. So we would be able to see the row boxes in this image. It is not clear here. And in the high pass filter, we get the transform, and after passing it to the high pass filter, getting the high images. This is the Fourier inverse of the input. Now we will talk how Fourier transformation work. So let us read. As we are only concerned with digital images, as we have talked, we will restrict this discussion to the discrete Fourier transform. Images, yes, images like in the real life we see the pair transfer images. Those are a combination of discrete points. So, so we are using discrete Fourier transformation here. The DFT is the sampled Fourier transformation and therefore does not contain a frequency forming an image, but only a set of samples which is large enough to fully describe the special domain image as we discussed. So here is the way how we can represent it. Here we are taking I and J like uh, two coordinates like representing rows and columns, and where FAB is the image in this spatial pointing to a particular point through which all the images formed, the combination of which all the images form, and the exponential term, which is the basis function corresponding to each point FKL in the Fourier space. The equation can be interpreted as the value of each FLK is obtained by the multiplying the spatial image with the corresponding base function and the result. So here we have talked explained more about this. Now next. These are the guidelines, means step to step how to perform this. So now first we start off by applying the Fourier transform on a particular image, like here it's shown. The magnitude calculated from the complex result is shown here. So here in Fourier transform, applying Fourier transform on a image, we only talk about amplitude. We don't talk about phase. So here we also are talking about amplitude of the frequency. So we can see that the DC value is far the largest component of the image. However, the dynamic range of the Fourier coefficients, that is the intensity value in the Fourier image, is too large to display on the screen. Therefore, all other values appear as dark. Yeah. And if you apply a logarithmic transformation to the image, we obtain this. Same we have described there for another example. So I think it's enough from my side. So thank you.